Dear students and other viewers and listeners, you are welcome again to this second part of today's lecture entitled Problem Solving with Computers. Friends, in order to put the things in context, let me recall some of the things which we discussed in the previous lecture. We first of all tried to define what is problem, what is its solution, to whom the problems are there, what is meant by a solution, etc. Then we further mentioned that during 1930s, a number of leading mathematicians and logicians proved that only a very small fraction of the problems under consideration or which can be encountered by the human beings can be solved with the help of computers. Then we told that in order to solve a particular problem, first of all we must be able to define it. And by definition we mean that we should be able to tell what is initially given to us, what is expected in order that the problem is solvable, that is what is the expected output. And besides this, we should also know what are the available means or tools for us. For example, if we have to find out the product of two very large numbers, say of 20 digits each, and if we don't have a pen and paper or pencil or anything, only our mind is there which is required to solve the problem, it may be unsolvable. So the unsolvability of a problem not only depends upon the initial position or the desired outputs, it also depends upon what are the tools are there with you to solve the problem under consideration. So after this discussion, we mentioned that the available tools in computers are just very elementary operations, like that it can accept an input in some textual form, or nowadays even in the graphical and other forms also, visual forms also. So that is one thing, that it can accept inputs. And then it can give an output also, because until unless a computer system is able to give output, whatever the solution it proposes, if it is not able to give it, it is useless. So the second capability of a computer system is to give output. And various available tools within the computer system are elementary operations like adding, multiplying, dividing, etc., taking square root, all these things. So when we say problem is unsolvable, we actually mean that using these operations, the problem is unsolvable. Tomorrow, if a computer system is embedded with additional capabilities which are not derivable from these elementary capabilities, then there may be more problems which may be solvable with the help of computers, even theoretically. So we must understand very clearly what is meant by solvable either by human being or by computer system or by society or by whatever it is. That is, the available tools play a very important role in deciding whether a problem under consideration is solvable or unsolvable. In this very context, we started with the taxonomy of the problems, because it is very important for us to understand what category the problem under consideration falls into. It is foolish to start solving the problem under consideration. And in view of the significance, I repeat from the very beginning the classification of the problems under consideration. For a brief minute or so, you look at the slide under consideration. Please look at the slide. The slide says that the problems may be divided into 4 or 5 categories which we will enumerate. The first category is that of the toughest problems which are maybe under consideration or which we may encounter. And those are not even recognizable problems. What are those problems? All possible negative consequences of a new technology. For example, urban pollution and ghettos could not be envisaged in the early stages as consequences of the automobile technology. Friends, today we say that information technology is very useful. Because it is a new technology, we are just bewitched by it. We are very much enamored of it. We are very much attracted of it. But how do we know that it is not going to have negative consequences at all? This is because we are not able to recognize the problems which may be there because of the information technology. Even now we are seeing some of the negative consequences of the information technology, like pornography. The child pornography is there. The bank heists are there, that the banks are looted of billions of dollars or rupees just at the click of a button. There are so many other things which are in the form of negative consequences of information technology. Even brainwashing, if we can go to that, that is, it is able to brainwash millions of people at the same time. False propaganda and all that can spread to almost everybody through the use of information technology. However, these problems are not being recognized at present because their dimension is very small. Even the privacy is being lost. So what I mean to say, there are a number of problems which of course are there, but those are not being recognized because their dimension is so small that when it takes a larger dimension, it becomes visible, it becomes being felt by the human beings, and then we say it is a problem. For example, the pollution, urban ghettos are a consequence, among other things, by the automobile industry. But when the initial cars etc. were developed, nobody thought that this type of situation, the pollution will be a big problem in cities. So this type of problems are called not recognizable problems. And when the problem itself is not recognizable, how can we solve a problem? So these are the problems which cannot be solved with even by human beings or machine or anything, because even the problems are not recognized. Then what is the next category? Please look at the slide for a fraction of a minute. Recognizable but not definable, even informally. That is, we recognize the problem. We know that there is something wrong. But we are not able to tell what is the situation at present, what is the situation when, if we reach into, then the problem remains no more. What are the available tools to us? All these things are required for the definition of a problem. In the case of economy, if the question is why the economy is not doing well, what is the initial state? Where from we start? Okay, this is the situation where each person is having this much income, etc., etc. We cannot determine this type of situation. And when we'll say that the economy is really doing well, can we define that when each and everybody is doing, earning more than this amount, then we'll say the economy is good? No, we can't say. And the most difficult part is, what may be the policies, what may be the other mechanisms of implementation and execution, which should be used in order to make the economy do well. Well, none of these things are known to us, despite the fact that we know, we recognize that economy is not doing well, the problem is recognizable but not definable. Again I emphasize, in order to solve a problem, whether with the help of computers or by the human beings, the problem should be definable. We must know what is the initial position, we must know what is the final position, and we must know what are the available tools with us. And any of these things, if it is not available with us, then we say the problem is not definable, and in that case, what to talk of solving the problem, we are not able to define the problem. So this is the second category of problems which we may encounter in our day. That is recognizable but not definable. Then there is a third category. Please look at the slide. The problem is definable but not solvable. This is third stage. Here you will be finding out that we are able to tell what is the initial position, and when we will say that the solution is there, and what are the means also are available to us. It is very famous in arithmetics or mathematics that any general equation of degree 5 or more cannot be solved using the elementary operations of addition, multiplication, division, subtraction and taking square root. Now in this particular case, when we are given an equation of degree more than 5 or so, we know what is the initial position. The initial position is an equation is given. ax square plus ax7 plus bx6 etc. is given, is equal to 0 is given to us. We also know what is meant by its solution. That if some values are suggested for the values of a, b, c, d, e, f, etc., the coefficients, and some solution is suggested, the suggested solution is actually a solution, then by substituting the values, we should be getting the two sides equal. So we know what is meant by a solution also. But still, despite the fact we know what is the initial position, despite the fact we know the final state, despite the fact that we know all the available tools, we are not able to solve the problem because there is no general method. So this is a third category where the problem can be even defined but not solvable. Please continue looking at the slide. There are a number of such problems in computer science which are studied under theoretical computer science. Please looking at the slide. Now, I'll take one or two examples, very simple examples of the problems which are not solvable. The earlier problem was just of the theory of equations, but let us take a very simple problem which I mentioned earlier also in my first lecture. Now the problem is to determine whether a particular person who is speaking and saying that I am telling lies, is he telling lies or not? This is the problem under consideration. We have to tell whether the person who is saying that I am telling lies, is he telling lie or is he telling truth? This is a very simple problem. And you know it is defined in every sense. A sentence in English is given, a question is given to us, and we have to find out just whether it is yes or no. So we know the proposed the expected outcome also. Only thing is the solution lies to give a definite yes or definite no. Now, but nobody is able to give us a definite yes or definite no in this particular case, despite the fact the problem is definable. I am telling lies, the person says, and if the person is actually telling lies, then this statement should be wrong. That is, he should be telling the truth. But if he is telling the truth, then it becomes wrong. So it is a vicious circle. These are generally self-referential problems. But my purpose here is that sometimes there are very simple looking problems may not be solvable. Here it is a very simple looking problem that I am telling lies, a person says, our problem is to tell whether the person is actually telling the truth or lies. So third category, I again enumerate the three categories so far discussed are, first of all, the set of problems which are not even recognizable. The second category is the set of all those problems which are recognizable but not definable. And the third category of the problem is which are definable but not solvable. So here this solvable stands for solvable by computer systems. Solvable by computer system means solvable by algorithmic means. So there are large number of problems which are definable but not solvable by computers' algorithmic methods. Then the next category, please look at the slides. The solvable problems. Anyway, there are large number of problems. Every day we are seeing that we claim that that problem is solved, the billing problem is solved, the railway reservation problems are solved. Large number of problems which cannot be discussed here. But what I want to say, even the problems which are claimed to be solvable, they can be further categorized into two classes. The first class of the solvable problems is that which consists of those problems which are only theoretically solvable. That is, when we come to their execution, in theory it says that it will be solvable after say 1000 years. So theoretically it becomes solvable. However, when we come to execution and see its practical utility, then the solution comes after such a time that its utility is over. For example, if we go for railway reservation for a train which leaves tomorrow, and if the answer comes after 10 days, then of course after 10 days we get that from this station to that station in the evening at this particular time a particular train goes. But what is the use of that? So this type of problems for which the solution may come at a very large, after a long time, or it may require large memory, etc., in a way which is not feasible. So this type of problems are called infeasible problems, though solvable but not feasible. And finally, there is a category of with which we almost deal in our everyday life, is the feasible, solvable problems. Must be definable, recognizable also. What are these? This is the category of problems for which the computer, using its elementary operations, gives a solution in reasonable amount of time. So friends, most of the time we are dealing with the last category only when we are thinking of solving problems with the help of computers. However, this doesn't mean that the other category of problems cannot be solved. No, in that case, we will have to use different methods apart from algorithmic methods. This only says that the rest of the category of the problems are either not solvable, or if solvable, are solvable in requiring large resources or time. So what is the way out? This doesn't mean that if algorithmic method is not available for solving the rest of the four category of problems, we stop. We don't attempt solutions at all. No, it is not like that. There are other mechanisms apart from algorithmic methods. And for that purpose, neural networks and other even artificial intelligence, etc., are there, where non-algorithmic methods are being used to solve problems, but with very limited success. What is so good about algorithms that we insist on algorithmic solution and we say no, as far as possible use algorithmic solution? Because it is very simple, step by step, it is very convincing also. When we execute an algorithm, the person who can read the algorithm can be convinced that whatever is solution suggested by the machine is really a solution. In other cases, when we toss a coin or something like that and we come to a conclusion, that may not be very convincing. I hope in view of this the importance of algorithm is there, but once again friends, I emphasize that apart from algorithm there are other techniques, for example artificial intelligence techniques in which we use heuristics, etc., shortcut methods, etc., and neural network which is modeled on the brain, and there are various other mechanisms available which are being adopted, but with limited success so far. As I mentioned in the very beginning, so far algorithmic method is the only methodology dominantly used in computer science for solving problems. So I hope we are very clear about the problems. Now repeatedly friends, I emphasized the role of the available tool, because I mentioned, please continue looking at the slide. I mentioned that the tool available under consideration makes a big difference to the solution of the problem under consideration. For this purpose, I give a simple example. For example, if we have to go to the moon, if we have got a spaceship available with us, then in that case, we say the problem is solvable. Whether it is actually solved or, you need not look at the slide please. The problem you need not look please. So, when we are going to the moon, and if there is no spaceship available, the same problem which is solvable is now no more solvable to us. So, the problem under solution or unsolvability of the problem under consideration is not at all, is useful only when the available tool is there. So friends, the available, I'll give you a number of examples here, that how the available tools under consideration make the difference to the solution methodologies. We will consider a problem of multiplication of two numbers. Please look at the next slide. Yeah, Okay, but before looking at the various examples, we will like to know the origin of the word algorithm. The slide says, algorithm is a description or statement of a sequence of activities that constitute a process of getting the desired output from the given inputs. It is a sort of formal definition. Now, it is very interesting how the word algorithm has come into picture. Actually, in 9th or 10th century in Iraq, there was a great mathematician called Al-Khwarizmi. Al-Khwarizmi actually compounded a lot of solutions which were step-by-step solutions and which could have been said. Please, no need of looking at the slide. Al-Khwarizmi compiled a large number of solutions suggested by the earlier generations, and he suggested some new solutions also, which were step-by-step solutions and which could have been called algorithm by the current definition. However, the word algorithm was not there at that time. So, what Al-Khwarizmi did is he compiled all the non-solutions which were step-by-step, etc. and he compiled all of them in the form of a book. Though that book was very popular with the mathematicians and other people, and gradually from Al-Khwarizmi, instead of saying the book by Al-Khwarizmi, people started calling it Al-Khwarizmi's method, and gradually it became algorithm in Latin and finally in English. So that is the interesting history behind the word algorithm. It is very important. Now friends, not every solution is entitled to be algorithmic, even if it is step by step. Because computer science is a formal discipline, a precise definition is very important in order to go ahead with any concept. So here we discuss 5 essential characteristics for a solution to be called algorithm. The first very important condition for a solution to be called an algorithm, I am differentiating between the two words, solution and algorithm. An algorithm is a solution provided the following 5 characteristics are there in the solution. The very first thing is the finiteness. What do we mean by finiteness? That is, first of all, in the proposed solution, the number of instructions must be finite only, because if you suggest infinitely many solutions, those cannot be computed by all the generations of the human beings or any. So it is no use of having a solution which has infinitely many steps. So this is the first requirement for a solution to be an algorithm, that it should have only finite number of steps. Not only finite number of steps, each step should be executable, should be carried out within finite amount of time. This is also very important. For example, if we are to write all the numbers greater than say 15, the algorithm may be very easy. Initialize a variable to 15, print the number, then you add 1 to the earlier number, then print the number, then you add another 1 to the number, so obtain, print it. So in the process, first we print 15, then we print 16, then we print 17. But we have not given any termination condition. Though the algorithm is just 3 steps. That is, first of all, you initialize a variable to 15, print it, add 1, and then go back to the first step. And in this process, you will be getting 16, 17, 18, etc., and each number is being printed. But until unless we tell where we have to stop. It is not an algorithm, it may be a solution. In the sense, you may go on printing the numbers from 15 onwards. But because it is not going to terminate, we don't call it an algorithm. This is the first requirement for a solution to be called algorithm. Next slide. Definiteness. Friends, here it is written, each step of an algorithm must be precisely defined. The action to be carried must be rigorous and unambiguous. What do we mean by this? By this we mean that if a step is there and if we are given some initial input and the step is executed, every time the same answer should come. For example, initially the value of a variable is 1 and we toss a coin, and if the coin is head, then we say that assign the value 3 to the variable, and if the tail is there after tossing the coin, then assign the value 4. So in this case, when you repeat the same problem's solution, what will be the number printed after executing these 2 steps? You may get different answers every time. Initially a variable is assigned value 1, a coin is tossed. If the head is up, in that case we assign the value 3 to the variable, and if the tail is up, then we assign the value 4. So after different experimentations of tossing the coins, sometimes the value of the variable will be 3 and at other times the value of the variable will be 4. This means we are not getting the same answer. Therefore, this sequence of steps is not a definite sequence of steps. This is meant by definiteness. Definite means if you give the same initial inputs and you execute an algorithm having definite sequence of steps, then it must give the same output for each given input. And I have clarified through the example of tossing a coin. So whenever we are using such a step as tossing a coin, the steps in the algorithm, in the solution are not definite. And therefore such a solution cannot be called an algorithmic solution. Then please look at the slide, next one. This is exactly the example which I have discussed just now. Please read it from the slide. I hope you have gone through the example. Then the next is also explains whatever I have already said. Number 3. An algorithm may have 0 or more inputs. Sometimes even there may not be any input at all. You may be knowing that for a particular computer, the largest number which can be represented in the memory of a computer and which can be printed out is already pre-assigned. So, this may be an algorithm, print the largest number. It may be a problem, print the largest number. In this case, the number of inputs is 0. So there are some situations or there are some problems in which you may not be required to give any input to the algorithm under consideration. However, there must be at least one output. That is very important. Because if we don't require any output from the system, what is the system used for? There is no use of the computer system if it is not required to give at least one output. So the number of inputs may be 0, but the number of outputs must be 1. It must be clear to everybody. And the next is effectiveness. Please, I have already enumerated 4 characteristics for a solution to be an algorithm. Namely, that first of all, each step must be finite. That is, it must take only finite amount of time in its execution and finite resources. And the number of lines or number of steps or number of instructions should be also finite. This is finiteness characteristic. Then the second is definiteness. I have said that if you include, you need not look at the slide, if you include tossing a coin, etc., then it is not a definite one. Then the third I mentioned that the number of inputs may be 0 or 1, and fourth I mentioned that there must be at least one output for a solution to be called an algorithm. And finally, the effectiveness. Friends, effectiveness is something that is whatever you do, you can do it with the pen and paper, etc. You may be definite, but the resources which are required may be so large that you may not be able to do that. Actually, finiteness may be a part of this one. For example, please look at the slide. The value of E may be computed in the way as is given on the slide. That is, E is equal to 1 plus 1 by 1 factorial plus 1 by 2 factorial plus 1 by 3 factorial and so on. Now, this way is one of the ways of finding the values of E. However, in order to execute this solution of the problem under consideration, you require infinitely many steps, which is not possible. And therefore, this particular method is not effective, and hence it is not entitled to be called an algorithm. So again I summarize, I summarize the 5 essential characteristics which are required for a solution to be called an algorithm are: number 1, first of all, each step must be finite and number of steps must be also finite in order for a solution to be called algorithm. Number 2, each step must be definite. That is, any instruction in the step should not be like this, that toss the coin and depending upon the value of the outcome, you should take the next step. This type of instruction should not be there in order for a solution to be called an algorithm. The third characteristic property for a solution to be called an algorithm is that the number of inputs may be 0 or 1. And fourth characteristic for a solution to be called an algorithm is that it must have at least one output, and that is very much desirable, because if computer is used as a tool to solve a particular problem under consideration, and if it is not required to give an output, it is useless. So this is the fourth requirement for a solution to be called an algorithm. And finally, I have told you the effectiveness. By effectiveness, in general, we mean that using a pen and a paper, a human being can execute that elementary step which is part of a larger solution to be executed by the computer system. In general, we can say effectiveness means this. So these 5 properties are the characteristic properties of a solution to be called an algorithm. So with this, friends, I have already enumerated this example. In the beginning, I mentioned that the available tools play a very important role in solving a particular problem under consideration. As I mentioned, the problem under consideration may be going to the moon. And if we don't have a spaceship available with us, the same problem which is solvable with the help of a spaceship becomes unsolvable. So in general, everyday life also, as I mentioned in the beginning also, that if we want to have a tasty pudding, we have flour with us, we have water with us, we have sugar with us. But if we don't have any utensil in which we cook, then the problem becomes unsolvable. So the availability of tools, whether it is a very complex problem or it is a very simple problem, availability of tools must be taken into consideration while discussing the solution of the problem under consideration. I elaborated this and how sometimes the solution is possible, but the efficiency is affected in the process because sometimes the available tools are too elementary, and because the elementary tools are too elementary, therefore it may be taking very large amount of time and in the process affects the efficiency. I explained with the help of 3 examples of multiplying 2 numbers. The first method which is used for multiplying 2 numbers, say m and n, is the usual ones. For example, please look at the slide. We have 2 numbers, 4, 26 and 37. We have to find out the product of these 2 numbers. So first method which I use or we use is just the usual one, in which we know the tables up to 10 of multiplication tables. We use these tables, and as is shown in the slide here, we get ultimately the solution. I need not go into the details of all this because it is very well known. Now the second method, the significance of the second method is that here the available tools are not that strong as were in the first method. That is, the person who is trying to find out the product of the two given numbers doesn't know the multiplication tables up to 10. However, the person has the capability that of counting and comparing two numbers. If two numbers m and n are given to the person, he or she can tell which is the larger one and which is the smaller one. And the second capability is that he or she can count also up to any finite number. Now in this situation, where the only two capabilities include counting up to a particular finite number and comparing two finite numbers, which one is greater and which is larger, we have to modify the solution. Now we cannot say that we use the multiplication tables in order to find out the product of two given numbers. So friends, here the algorithm, if it exists, as I mentioned in the very beginning, for every given problem there may not be an algorithmic solution. However, here fortunately there is an algorithmic solution which I narrate in few words. What we will do it, we use two sheets of papers. On one sheet of papers, and the two given numbers to us are m and n, and the problem under consideration is to find out the product of the two numbers, that is m dot n. One of the methods, keeping in view the capabilities of the person solving the problem or the tool or system whichever is attempting to solve the problem, is having two sheets of papers. I use a human being's example. A pencil is available, two sheets of paper are available. On the first sheet of paper we make a mark, and whenever we make a mark on the sheet which is on, say, on the left hand side, we make n marks on the right hand side. Then we make another mark, but before making another mark, we compare this number of marks already made on the sheet with the given number m. If the number of marks already equal to m, then we'll stop the process and count the number of marks on the right hand sheet. So we suppose m is 4, then in that case first we made one mark, and m is 4 and n is say 15. And corresponding the first mark on the left hand sheet, we'll make 15 marks on the right hand sheet. Then we make another mark on the left hand sheet. Now the number of marks present on the left hand sheet is 2, which is compared with 4. Because 2 is less than 4 and the person is capable of comparing these two numbers. Therefore, the process is repeated on the right hand side. That is, another 15 marks are made on the right hand side. Once the 15 additional marks are made on the right hand side, then we come again to the left hand side sheet. And there we make another mark. And now we count the number of marks which is a part of the capability of the given capabilities of the person. Now the 3 marks, 3 is less than 4. Therefore, the process of making 15 marks on the second sheet is repeated. Now we make another mark. We get 4 marks, but 4 is also less than equal to 4. Therefore, again the process is repeated. Then we make another mark. But now 5 marks are there, which is more than 4. Therefore, the process is terminated, not terminated. But then the next step, the final step is to count the number of marks on the right hand sheet, which gives us 60. So friends, the purpose is not to solve the problem like this. The purpose is to tell you that once the available tools are different, the algorithm or the method of solution has to be different, and it may be very complicated. I give another very well-known method for solving this problem, which is called Larousse method, which was used by the peasants in Russia. Who used this method? They were capable of multiplying and dividing any number by 2. So just with this capability and comparing two numbers. So with this capability, how they were able to solve the problem, please look at the slide. Yeah. Here, please look at the slide. Because we want to explain it briefly, not taking much time. So instead of larger numbers, we are taking two numbers, 45 and 19. So the method was, because the capability of the person under consideration or the system under consideration are, in addition to counting, in addition to comparing two numbers, the person also has the capability of being able to divide by 2 and multiply by 2. So how, using only these capabilities, a person is able to find out the product of two numbers? First of all, the number in the first column is divided by 2. First of all, it is found out whether it is 0 or not. If this is a number 0, then the answer comes out, which is available in the partial result. The values of the first, second, etc. are initialized. The first is 45 here in this particular instance, second is 19, and the partial result to begin with is 0. Because the number is 45, which is not equal to 0, it is divided by 2. And on division of 2, we get the quotient 22 and the remainder 1. Now the algorithm says that in case the remainder is 1, then you add second to the partial result. Now the second is in this particular case 19. Therefore 19 is added to the partial result, which is 0, and we get 90. And now we will go ahead with the quotient, which becomes now the first number. Now we have the quotient as 22. The capability allows us to divide it by 2. Therefore, we divide 22 by 2. We get the quotient 11, and the remainder is 0. And in case the remainder is 0, we don't do anything. So we go to the next slide, and here the remainder is 11, the second becomes, and every time, every time whenever the first number is divided by 2, the second is multiplied by 2, and it is very natural. On one hand we are dividing by 2, and on the other hand the second number is multiplied by 2. And whenever there is a remainder of 1, then the second is added to the partial result. And we can see ultimately we will be getting the desired result, which is in this particular case 152. So the whole exercise or whole of this explanation is meant to explain the significance, the importance of the available tool in consideration. These are very simple examples. But in the case of computers, where various type of problems are required to be solved, various type of available tools have to be taken into consideration, and depending upon the available consideration, only then we should go ahead with the solution. Otherwise, as I mentioned, in view of the fact that the inbuilt capabilities of a computer system are very elementary, it can read a number, it can give output, it can read a given input, it can give an output, and in addition to that, it has very elementary capabilities, in which, among which the arithmetic capabilities are just capability of adding two numbers, dividing one number by another, multiplying and subtracting, taking square root, etc., etc. These are the very elementary. And if I go still further, these are too much actually. The elementary capability of a computer system is not even that much. It can add only a 0 to 1, a 0 to 0, a 1 to 1. These are the basic. Rest of the addition capabilities are obtained as a sequence of steps of these elementary capabilities. So whenever we say a problem is not solvable by the computer system, it is always meant that whatever are the inbuilt capabilities, in terms of that, if we use a sequence of steps, then the solution may not come out. So with this, friends, I hope you must have understood the basic idea of how to solve problems with the help of computers. In addition to whatever capabilities I have mentioned, there are 2 or 3 other capabilities also, about which we will talk sometimes later. Thank you very much.